This is going to be our third podcast in our series on bone, and in this podcast we're going to talk about bone formation. Before we do that, let me make just a few comments about the bone matrix. There's an organic component to the bone matrix which gives the bone its tensile strength, and there's an inorganic component to the bone matrix that gives the bone its compression strength. The organic component essentially consists of collagen type 1 and the ground substance, and together these constitute about 25% of the bone matrix. You can see that the collagen type 1 is 90 to 95% of the organic component. The inorganic component of the bone matrix essentially consists of hydroxyapatite crystals and then citrate, carbonate, fluoride, and magnesium salts. Now, when we talk about bone formation, we're talking about ossification, and bone forms or develops in the fetus. And in the fetus, we can talk about two distinct types of bone development. We can talk about endochondral ossification or endochondral bone development, and that's on a cartilage model. As you know, most of the skeleton in the fetus is cartilage, and endochondral bone formation is very important for the development of the extremities, for the development of bones like the vertebrae, the pelvis, and the ribs. And then there's also a process called intramembranous ossification in the fetus. That's where you have differentiation of bone directly from mesenchymal cells, and the flat bones, like the bones in the skull or the face, the mandible, or the clavicle, develop from intramembranous ossification. Now, as we said in the last podcast, osteoblasts elaborate the bone matrix. Initially, the matrix is non-mineralized, so the osteoid, as it's initially laid down, is not mineralized. The osteoblasts induce precipitation of hydroxyapatite, and the bone will grow by appositional bone growth as the bone is remodeled, because you're going to get constant bone remodeling even in the fetus once the bone tissue is laid down. We can talk about immature bone and mature bone. Immature bone, sometimes called primary bone, is also known as woven bone. That's the initial bone that's laid down, and here the bone matrix fibers are arranged more randomly. In lamella bone, the mature bone would replace the woven bone. That you can think of as the adult form of bone. There the lamella are laid down in a very regular or concentric manner. Now, as we said, intramembranous bone formation occurs in the flat bones. The osteoblasts differentiate directly from the mesenchyme. They lay down interconnecting spicules of bone. The periosteum continues bone deposition. Bone remodeling will occur, so woven bone that's initially formed is going to be replaced with lamella bone. And the image on the left is a histological section of intramembranous bone, and you can see the bone spicules here. The cartoon tries to depict what occurs in intramembranous bone formation. You've got these mesenchymal cells that coalesce into a blastema, and the osteoprogenitor cells develop directly from those mesenchymal stem cells. They become osteoblasts, and the osteoblasts lay down the developing bone matrix. And here the cells get trapped into lacunae as osteocytes. Endochondral bone formation also occurs in the fetus, and we're going to describe endochondral bone formation. In the long bones, this is as the bones develop on a cartilage model. Chondrocyte differentiation from mesenchyme, synthesis of collagen type 2, that's occurring by interstitial and appositional bone growth. That's all part of the cartilage model, but you are eventually going to have a conversion of the cartilage model in the fetus to bone. Here the perichondrium is going to differentiate into a periosteum as you form a bony collar. There's a conversion in the synthesis of collagen by the chondrocytes. They begin to synthesize collagen 10, which initiates calcification of the cartilage matrix. That causes the chondrocytes to hypertrophy and die. As the chondrocytes are hypertrophying, they're synthesizing and secreting growth factors, notably vascular endothelial growth factor. That causes a blood supply to invade the cartilage matrix. That blood supply carries osteoprogenitor cells, which are going to differentiate into osteoblasts, and osteoblasts will synthesize and secrete collagen 1. As the matrix calcifies, you cannot get diffusion. Remember, the chondrocytes can only survive by diffusion. The matrix calcification will serve as a substrate for appositional bone growth. Now what I'm going to do is first show you some histological images, and then we'll describe the process. So this is showing bone growth probably in a proximal or intermediate phalange in a fetus, and actually this is a section of the whole finger as a longitudinal profile. You can actually see the stratified squamous epithelium on the surface. You can see some of the dermis. You can see probably glands in the dermis, but here's the bone itself, and here's the cartilage model. This cartilage is going to be converting to bone during endochondral ossification. What I want to do now is show you some high-power histological views in these different regions. So first you have a zone of reserve cartilage. Here you can see the individual chondrocytes in the lacunae. This is hyaline cartilage. The cartilage model for endochondral ossification is hyaline cartilage, so this is exactly like hyaline cartilage that you've seen in the zone of reserve cartilage. Here is the zone of proliferation. The chondrocytes stack on top of each other as they're dividing, so you see these isogenous groups. This represents the zone of proliferation as the cartilage is dividing in the growing fetus. Here you have a zone of hypertrophy. The cartilage cells are getting larger and larger. They're eventually going to start dying as there's a conversion of collagen synthesis from collagen 2 to type 10 and the cartilage to collagen type 1, characteristic of the bone. Eventually the cells are going to calcify. Here we see the zone of calcification and reabsorption. You can see some of the zone of calcification here. You see it here as well. Here is the cartilage. Notice there are no chondrocytes here because they've died. Here is some of the bone forming. So these are osteocytes within lacunae. This is a mixed bony spicule. Look at this. Here's actually an osteoclast. There's an osteoclast here on the surface, an osteoclast here on the surface, and you can clearly see the marrow cavity. This diagram we're going to come back to multiple times as we talk about endochondral ossification. A couple of points I want to make from it. First, as you know, in the fetus, the long bones develop on a hyaline cartilage model. So hyaline cartilage on this diagram is shown in blue, areas of calcified cartilage shown in purple, and then kind of the yellowish color is showing the areas as bone is forming. So we're going to be talking about endochondral ossification occurring, and then we're going to talk about bone development and bone growth as you get later into fetal life. And this bone growth actually continues from maybe the third, fourth month in fetal life all the way up until puberty. So let's talk about the stages of endochondral ossification. So we talk about the cartilage model of bones in the fetus, and that's depicted here in image 1 on the diagram. We then talk about the fact that a bone cuff forms as osteoblasts are now forming in the perichondrium, the connective tissue around this cartilage model. And this begins around 12 weeks of development. This perichondrium is going to convert to a periosteum, and you're going to have an osteogenic layer. And we define this region in image 2 as the formation of the bone collar. Now the chondrocytes in the mid-region of this fetal bone are going to become hypertrophic. The cartilage matrix is going to start to be reabsorbed. The chondrocytes are going to secrete alkaline phosphatase. That's going to stimulate the cartilage matrix to calcify. The calcified cartilage matrix, as you might imagine, is going to inhibit diffusion of nutrients. Thus the chondrocytes are going to die. The cartilage matrix is going to break down. The lacunae are going to become more confluent. That's going to lead to a larger cavity, and blood vessels are going to grow through the bone collar to vascularize this cavity. So that's shown here as the cavity is getting bigger in image 3, and the blood vessels coming in to vascularize it in image 4. As you might imagine, mesenchymal stem cells follow the path of blood vessels, and so they're going to differentiate into osteoprogenitor cells within that cavity. Those osteoprogenitor cells are going to contact the calcified cartilage spicules, and they're going to differentiate into osteoblasts, and that's going to be defined as the primary ossification center on these mixed spicules. You're also going to have hematopoietic stem cells gaining access to the cavity, and so you're going to initiate bone marrow activity, and that's shown in image number 5. Here is just an image, a histological image of a mixed bony spicule stained with Mallory Azon stain. The cartilage here is shown in the lighter blue. Note there are no chondrocytes visible in the lacunae here because the chondrocytes have died as this cartilage is calcifying. The bone, the matrix is shown in a darker blue. You can see the osteocytes trapped in lacunae. If this was an H&E staining, the cartilage would be more basophilic and the bone itself would be more eosinophilic. Now, endochondral bone growth is actually going to begin in the second trimester, and it's going to last through puberty. And as we describe endochondral bone growth, essentially the diaphyseal marrow cavity is going to enlarge, and epiphyseal cartilage is going to begin to be oriented in these distinct zones that we showed you earlier in the histological images. The chondrocytes are going to divide in the zone of proliferation. They're still going to synthesize collagen II. Chondrocytes in the zone of hypertrophy are going to start synthesizing a different collagen. And vascular endothelial growth factor. This VEGF is going to initiate vascular invasion of the secondary ossification center on the proximal end of a long bone, and that's going to form a new marrow cavity. So we're seeing those described in images 6 and 7. So here you're getting a secondary ossification center forming as blood vessels come in and this new marrow cavity forming. The cartilage matrix is going to calcify. The chondrocytes are going to begin to degenerate in this zone of calcification. The cartilage is going to be reabsorbed, and primary spongy bone is going to remain in the zone of reabsorption. The secondary ossification centers are forming on the distal end of the long bone. As the secondary ossification center develops, the only cartilage that's going to remain on this hyaline cartilage model of the fetal bone is going to be the articular cartilage on the ends of the bone and a transverse disc of cartilage, which you know of as the epiphyseal growth plate. And the epiphyseal growth plate is shown here on the diagram, and here you can see the articular cartilages on the ends of the bones. Now, something you should be aware of, the bones are going to grow proportionally due to external and internal remodeling. The thickness of the epiphyseal plate is going to remain constant during bone growth, so the amount of cartilage produced at the zone of proliferation is going to equal the amount of cartilage that's reabsorbed at the zone of resorption. As new cartilage is produced, the epiphysis is going to be pushed away from the diaphysis. And when individuals achieve maximal growth, proliferation of new cartilage within the epiphyseal plate is going to terminate. And so that's shown in the images 9 and 10. So here on image 9, an epiphyseal plate has closed. Here on the distal end of the bone, on the proximal end of the bone, the epiphyseal plate is opened. Here it's showing both of the epiphyseal plates closed. And at this point, you're not going to have any more bone growth. All you're going to have is the articular cartilages remaining on the ends of these long bones. This is a diagrammatic view of a secondary ossification center in a metatarsal bone. Here is the primary ossification center in this metatarsal bone. The primary ossification center here is much more active than the secondary ossification center. Because there is an epiphyseal or secondary ossification center, the zone of reserve cartilage is more diminished here, but you can still see the zones of proliferation, zone of hypertrophy, and the zones of calcified and cartilage reabsorption here. You can see osteoblasts on the surfaces, and eventually the osteoblasts will become trapped in lacunae. Now, this is an important concept. Bone growth is going to require remodeling to maintain the original proportions of the bone. So here is bone growth before remodeling is occurring, but as the bone is growing, there's constant remodeling. So you're reabsorbing bone on some surfaces while you're depositing bone on other surfaces, and this reabsorption and deposition of bone is going to be proportional, so that as the bone grows, here you can see, for example, you're adding bone on this surface and on this surface, whereas you're taking bone away on this surface and on this surface. So the bone is growing in a proportional manner.